Welcome to our chemistry lab. Today, we are using copper and three different metals, and aluminum and magnesium to measure and compare their cell potentials.
We've prepared 0.10 of copper to nitrate and 0.10 of zinc nitrate solutions. Here's alkyl salt-breaking filter paper soaked in potassium chloride to allow ions to flow between the half cells. After inserting copper and zinc strip into their solutions, we connect the bridgeless. The voltmeter reads 0.48 V, showing zinc oxidizes and copper ions reduce.
Here we will use KCl again as a salt bridge, which goes the same for the other experiments as well. Once my partners places the strips and we hook up the bridge, the voltmeter reads 0.50 UV, indicating aluminum oxidizes while copper ions reduce. KCl is used again as a salt bridge for this one as well. Here's the KCl salt bridge, which the filter paper soaked in potassium chloride to complete the ionic circuit. After my partners puts the ribbons into their solutions and we connect the bridge, the voltmeter reads 0.75 V, showing magnesium oxidizes and drives copper reduction. And now we compare these to the theoretical values calculated using the formula, in which our actual values are lower than expected due to electrode surface oxidation. These are our results: copper magnesium to 0.70 V and copper aluminium to 0.0 V, and finally copper zinc 1.10 V.
Hello guys, this is Mohaimen and I will try to explain how we electroplated a carbon rod using copper in an electrolytic cell. At first, in a 100 ml beaker, we took 50 milliliters of copper sulfate solution as electrolyte. As anode, we chose a copper strip which weighs 0.875 grams. And for cathode, we had a copper electrode which weighs 1.761 grams. As for the connections, the red wire that is attached with the anode is connected to the positive side of the cell so that electrons can travel from the anode towards the cell. As for the black wire where the cathode is connected to the negative part of the cell so that electrons can travel from the cell towards the cathode. After connecting everything, we put the current to 0.5 amperes, and throughout the process it was somewhat the same. As for the voltage, it fluctuated between 5 and 6, but it doesn't hamper our experiment. At anode, oxidation of copper is taking place where copper ions are being released into the solution and the electrons released are traveling from anode to the cathode. At cathode, carbon rods are acting as simple conductors. So when electrons gather here, the copper ions floating in the solution bond with the electron, forming a solid copper. This reduction reaction of copper causes it to accumulate at the cathode surface. Just for a quick mention, you can see the copper rod breaking at this point of the video. After 20 minutes of electroplating process, we see a thick layer of copper is visible on the surface of the cathode, and we see that the anode has become thin. These are their final masses. Now using this formula, we find the theoretical value and find out the obtained value. Now we find the yield. Our yield is 67%, which can be for the following reasons: loss of metal in salt solution, impurity of copper strip or copper sulfate solution, accumulation of copper at the bottom of the beaker, incorrect weighting, incorrect time calculation, faulty conductors, or faulty cell. Hopefully you liked this experiment. Now we will move on to Meriam's experiment.
Hi everyone, today we're exploring an exciting electrolysis experiment using potassium iodide. We'll set up an electrolytic cell, observe chemical changes at the electrodes, and talk about the science behind it all in under 5 minutes. Here are our materials. First, we seal the bottom of the U tube with a small piece of cotton wool. Then, fill both sides with Kl solution until they're both 1 to 2 centimeters from the top. When we insert carbon electrodes into both ends, we ensure the metal clip stays out of the solution. Now we connect the electrodes to a DC power supply and set it to 9 to 10 volts. This starts the non-spontaneous electrolysis reaction because we're adding electricity to make it happen. After 5 minutes of running the reaction, we notice changes. At the anode, the positive electrode, iodine ions, lose electrons and form iodine. The anode reaction, which is oxidation, you'll see a dark color here once we add starch. It reacts with the iodine to form a blue-black complex. At the cathode, the negative electrode, water is reduced, forming hydroxide ions and hydrogen gas. The cathode reaction is reduction. Now let's calculate the cell potential. Because the value is negative, this reaction is non-spontaneous. That's why we use at least 1.37 volts, though we provide a 9 to 10 volt to ensure it proceeds effectively. Now, let's break down the roles of our special materials. Starch reacts with iodine to reveal a dark blue color. Phenolphthalein, or universal indicator, helps detect pH change. Pink or purple at the cathode means it's basic. Carbon electrodes are inert. They don't react, just conduct electricity, keeping the focus on the electrolyte. Electrolysis is used in water purification, electroplating, and even metal extractions, but it uses a lot of electricity, so it's important we power these processes sustainably to reduce environmental impact. That wraps up our Kl electrolysis experiment. We saw oxidation at the anode, reduction at the cathode, and how indicators reveal chemical changes. Thanks for watching and keep experimenting.
All right.